Some Lewis structures, however, are not going to be so easy to draw. And they may follow the octet rule, but if you just try to draw the dots and figure out, this element usually forms 4 bonds, this one forms 2, you're going to run into some issues and not really know how to deal with them. And it's because molecules can form that contain something called a coordinate covalent bond. It's also sometimes called a dative covalent bond. In this type of bond, both electrons in a bond actually come from one of the atoms. So unlike where they each contribute 1, in a coordinate covalent bond, both electrons come from one of the atoms. And so it can be a little tricky to figure out exactly how they go together. So carbon monoxide is sort of a classic example where people try to draw it and they get stuck. So carbon has 4 valence electrons, and you should associate carbon with normally forming 4 bonds. Oxygen has 6 valence electrons, and so going into it, we would expect oxygen to form 2. Now this molecule exists, and I'm trying to explain how it might do that, but it's really hard to reconcile that carbon wants to make 4 bonds and oxygen wants to make 2 bonds, and so that doesn't really work for either of them. If you started to go through the motion, you'd share those electrons, you'd share these electrons, but now oxygen is already satisfied, and yet carbon does not have an octet. So what's going to happen is that actually these 2 electrons from oxygen, the only way that this molecule works is if the 2 electrons from oxygen actually get donated to the carbon and are shared by both. So that's how a coordinate covalent bond could form. Both of those electrons came from the oxygen atom and now are being shared by both in a covalent bond, and that's what gives the molecule more stability. So in the end, the Lewis structure for carbon monoxide looks like this. There's actually a triple bond, and both have a lone pair. So it's very odd. It's a very weird structure, and that's sort of hard to come up with on your own. So this video is going to focus on what I like to call my 7 steps to freedom. But what I mean is it's freedom from stress, and it's going to help you really make any Lewis structure easier to figure out. So if we were going to do the example of carbon monoxide, I'll use it as the example to walk through the steps. The first step of the 7 steps is to add up the total number of valence electrons needed by these atoms if they were to feel like they had full octets or full outer shells. Usually, this number is going to be 8 electrons for each atom. So carbon, if it wants to feel like it has 8 valence electrons, and oxygen also wants to feel like it has 8 valence electrons. So in the end, when we bond, the point of bonding these 2 atoms together is that they're each going to feel like they have this many electrons. So in total, we need to feel like we have 16 valence electrons. So step 1, add up the total number of valence electrons needed to give full outer shells for each atom if they were separate atoms. Number 2, add up the actual number of valence electrons that you have to work with. Well, carbon has 4 valence electrons and oxygen has 6 valence electrons. So that means I actually have 10 electrons to work with. Okay, so I need to feel like I have 16 electrons, yet I only have 10 to work with. So in order to figure out the number of electrons that need to be shared, I just subtract those 2 numbers. 16 minus 10, that means I need to share 6 electrons. Well, there's 2 electrons in every bond, therefore the number of bonds equals 3. Okay, so with a very simple mathematical steps, without doing any of that tricky work on the previous page, I now know that I need to draw 3 covalent bonds because mathematically that's the only way to make both atoms feel like they have that full octet. So now I draw the covalent bonds, step 5. So in this case, there's only 2 atoms, so all 3 bonds must go between those 3 atoms. And then number 6, add in non-bonding electrons. So now I need to make sure that every atom has its full octet. Right now, carbon feels like it has 6, so I give it a lone pair. Oxygen feels like it has 6 as well, so I give it a lone pair. And now they both feel like they have 8. Step 7 is double check. Go back to step 2. Step 2 told me that I had 10 electrons to work with, and check if you actually used 10 electrons. 2, 4, 6, 8, 10. So I've used 10 electrons, I've given each atom an octet, and therefore I've drawn a correct Lewis structure. Okay, we could do this really on any of these. The only difference is when you do this with hydrogen, you need to remember that hydrogen only needs 2 valence electrons to feel like a full outer shell. Therefore, it changes this first step. So let's try it with H2O2, which is sort of a funny molecule. This is hydrogen peroxide. So every hydrogen feels like it wants to have 2 for its outer shell, and I have 2 of them. So that means the hydrogens need to have 4 valence electrons. Every oxygen, 8 full outer shell times 2 is 16. So in total, we need to feel like we have 20 electrons. All right, well, how many do we have to work with? Each hydrogen has 1, 1, and 1. Each oxygen has 6, 6, and 6. So I've got 12. I've got 14 to work with. So I need to feel like I have 20. I actually have 14, which means I'm going to need to share 6. And that means 3 bonds. So now I know that I need to have 3 bonds. Well, I know that hydrogen only ever forms 1 bond. So that's kind of a helpful thing I get to use. So hydrogen must bond to this oxygen. And then probably for the sake of symmetry, the other hydrogen will bond to the other oxygen. So 1 hydrogen per oxygen. So I need 1 more bond. That means that third bond must go between the oxygens. Now, if I need to give everything their octet, I need to give 2 lone pairs to each oxygen, because right now they only feel like they have 4. And now I can double check. Hydrogen has 2, this oxygen has 8, this oxygen has 8, and this hydrogen has 2. And if I count up, I've used 2, 4, 6, 8, 10, 12, 14. I've used the number of electrons that I was allowed to use. So the 7 steps, take them or leave them. You can use them, but there are definitely going to be some tricky examples going forward. And if you get stuck on how to draw it, it's a simple way to mathematically figure out how many bonds you must draw in a structure. Obviously, you can't use the 7 steps for the exceptions, the beryllium and the boron. You really just have to memorize those 2 elements as creating the strange exceptions to the octet rule.